Okay, we can get started. In the last lecture, we talked about a special type of bialgebras that are obtained from what is called a coboundary type of coproduct. So remember that the bialgebra is really a Lie algebra equipped with a linear map that goes from G to G tensor G, so that the dual map from G star tensor G star to G star is a Lie algebra map. It's like a Lie bracket, makes G star a Lie algebra. And this map delta and the Lie bracket of G, they have to talk to each other via this co-cycle relation, which we had in the previous lecture. Lecture 21. Okay, this is the co-cycle relation. All right, this relation describes the relation between delta and the Lie bracket of G. In other words, it describes the relation between the Lie bracket of G star and the Lie bracket of G. All right. And now the question is how to construct such deltas to make a Lie algebra indeed a Lie bialgebra. And well, one way was to define delta to be of the form x acting on a 2 tensor, where a 2 tensor means an element of the vector space G tensor G. It can be written as a finite sum of the form ui tensor vi, where ui and vi are in G, and the action of x on a 2 tensor was defined according to so-called Leibniz rule, which is this rule. The explicit form of it is this one. And then we learned that such a delta R always satisfies the co-cycle relation. So then that becomes the sort of that complicated part becomes easy. But then in order to get a Lie bialgebra, we need to make sure that we have the antisymmetry and the Jacobi identity for delta star corresponding to this delta. And those will correspond to the following relations. This antisymmetry corresponds to the skew symmetry of this tensor. In some sense, it says like R12 plus R21 is G invariant. And the Jacobi identity turns into this relation being G invariant, the so-called, sometimes they call it the Schouten bracket, or this vanishing of this expression is called the classical Yang-Baxter equation. And we also learned about an application of the classical Yang-Baxter equation in representations of braid groups. Okay. Are there any questions about the last lecture before we continue our endeavor in the world of Lie bialgebras and learn a bit more about them? So the most, so like one of the most important results, I would say, or like most fundamental results in this theory is that the correspondence between Lie groups and Lie algebras can be extended to a correspondence between Lie bialgebras and Poisson structures on the corresponding Lie group G. Okay, so let me first well, we can I mean, let me first define what a homomorphism of Lie bialgebras means, and then I'll describe these correspondences. So let me give a definition. This definition is pretty straightforward. When you think about it, it's the most natural thing you can do when you have a structure like a Lie bialgebra structure, but let's just make sure we're all on the same page. So a homomorphism of Lie bialgebras like phi that goes from G comma delta. Remember, G is the Lie algebra, delta is the dual of the bracket, to H delta, and I just write delta sub G and delta sub H to sort of distinguish two deltas. Okay, so what is it? It's a Lie algebra homomorphism. That also preserves the bialgebra structure, which means the delta. In other words, that it satisfies the following relation. Phi tensor phi of delta G equals delta H of phi. So where does this relation come from? Well, we just have to think about where these maps are. So we have this map phi that goes from G to H. It's a bialgebra homomorphism. But we also have these deltas. And now if we are given phi, what's the most natural map we could put from G tensor G to H tensor H? You just tensor on each factor. So this is the map. So this phi tensor phi, to be more like maybe specific, the phi tensor phi, it maps sigma xi tensor yi, where xi's and yi's are both in G to sigma phi xi tensor phi yi. And you can check linearity of phi will turn into well-definedness of this map. Okay, you can check that this map is well-defined. We basically have to check the some bilinearity property. Okay, and now this relation up here basically says that this diagram commutes. If you first apply phi and then delta H, it will be this side, and if you apply it the other way around, it will be this side. Okay. All right, so it relates the product of the Lie algebra to the product and the coproduct to the coproduct in this sense. All right. So now these correspondences between Lie bialgebra structures and Poisson-Lie groups are materialized in the following results, which are originally due to Drinfeld. So the first person to discover them is Drinfeld. So the first theorem is that if G delta is a Lie bialgebra, and G is the connected and simply connected Lie group associated to that, which means the Lie algebra of capital G is G. So we know that capital G exists. This is one of Lie's theorems. We discussed this theorem, but we didn't prove this in this course. But anyway, such a thing exists. All right. So then, so at the moment, capital G doesn't depend on delta. So capital G is this Lie group, which is simply connected and connected with Lie algebra G. Okay. But now this delta can be lifted in some sense to a Poisson structure on G. In other words, there exists a unique Poisson-Lie group structure on G such that it corresponds to delta. So in what sense does it correspond to delta? We discussed this a few lectures ago, I think maybe in lecture 21. So that's basically roughly after we talked about Poisson-Lie groups. Okay, so yeah, here. Okay, yeah. Maybe just before. Okay. Yeah. So if you have a Poisson-Lie group, we associate it with a Lie bialgebra structure, right? So in other words, on its Lie algebra, we obtained a Lie bialgebra structure in such a way that we just, well, what do we need to get the Lie bialgebra structure? We need a Lie bracket on G star, which talks nicely to the Lie bracket of G. How do we get this Lie bracket on G star? We basically defined it by this formula, by this underlying formula. We took two elements in G star. We want to define their Lie bracket. It should be another element of G star. We think about these two as derivatives at identity of two smooth functions on capital G, and then we use the Poisson bracket of capital G and differentiate it to get another vector in G star. Okay. So this, in this sense, we went from a Poisson-Lie group to a Lie bialgebra. And now this theorem of Drinfeld says that you can actually go in the other way, in the other direction, assuming that capital G is simply connected and simply connected. Okay. All right. So this is the first result. And now you can ask, what about the correspondence between Lie subalgebras and analytic subgroups? What happens there? So, or rather, what about correspondence between homomorphisms between Lie algebras and homomorphisms between Lie groups? Can we do a bialgebra and Poisson version of that? So this will include the sort of Lie group Lie algebra in sort of a statement, because those you can think about as embedding of a Lie algebra into another and embedding of a Lie group into another. Okay, so here's the theorem. Uh-oh. So let G and H be Poisson-Lie groups. Now a homomorphism like capital Phi from G to H of Poisson-Lie groups, which means a Lie group homomorphisms, a Lie group homomorphism which preserves the Poisson structure. It's compatible with the Poisson structures. So it corresponds, or rather it induces a homomorphism of Lie bialgebras like Phi underline going from G to H. In other words, when you take just a derivative map, which is the Lie algebra homomorphism coming from this capital Phi as a Lie group homomorphism, you can dualize it to get a map from G star to H star. And now this will be again a Lie algebra homomorphism. Okay, or you could think about the co-product. Then you have this map from G to G tensor G, and like H to G tensor, like H to H tensor H, and again, you have a commutative diagram just like before. Okay, you can think about it in both ways. They're really equivalent. Okay, maybe I should write i.e. commuting with delta G and delta H in a suitable sense. Okay. And furthermore, just like in the case of Lie groups, where a Lie algebra homomorphism could be lifted to a Lie group homomorphism when the domain was simply connected, here we can do the same thing for the bialgebra context. In other words, if, maybe I should write furthermore, if G is connected and simply connect it. And phi going from G to H is a Lie bialgebra. Homomorphism then there exists a unique Lie group homomorphism, which is also a Poisson-Lie group homomorphism. I mean, which all respects the Poisson structure. Poisson-Lie group homomorphism such that when you take its derivative at identity, you end up with this map phi, little phi. Okay, so again, this is a result of Drinfeld. I forgot to say. All is good so far? Okay, so in some sense, we have more structure, but we have an analogous theory, which is very important and beautiful. Okay. So the next thing I want to talk about is that so let us try to write the relations between the Lie bracket and this delta, which is on the dual, in sort of a more sort of a formal way to see what it says. Okay, so maybe okay, so a formal way, the more formal way of writing the cocycle identity, the cocycle relation for delta. Okay, so suppose that I have a Lie algebra, which is indeed a Lie bialgebra. So it has a Lie bracket, which one can think about as a linear, as a bilinear map on G with values in G, or equivalently a linear map from G tensor G to G. And it also has some delta, this co-product that goes in the opposite direction. Okay, so what is the relation in terms of beta and delta that describes this cocycle relation? So I want to just use minimal notation, not use any brackets or anything, just use beta and delta as much as possible. Okay, so we could start. So I mean, let me remind you of this the cocycle relation, and then we can try to sort of write this in the more general form. So so we have this is equal to x delta y plus delta xy. So now, if you want to write the left-hand side, so what is happening on the left-hand side? Well, we have G tensor G, and then we apply the bracket, which is beta. And then we are applying this delta. Okay, so the left-hand side, I could just write beta O delta. Okay, as a map from G tensor G to G tensor G. And now I want to describe the right-hand side as a map from G tensor G to G tensor G. Let's see what happens there. So again, I have this x delta y, so I can start from some element in G tensor G, like x tensor y. And this time, first, I have to apply delta to the second component. So I should do identity map tensor delta to end up with x tensor delta y, noting that this is now an element of G tensor G tensor G. So this is really a 3 tensor. Okay. And now I should do two things, because this one term, this x should act on the first factor of delta y, tensor the second factor, plus x acting on the second factor, tensor plus like tensor the first factor. So there's two ways to proceed. The first way, if I think about this as a sum of R tensor S's, I should get XR tensor S. And for this, I have to apply the Lie bracket to the first component. So I should do beta tensor 1, which will put me in G tensor G, and that's good. For the second one, though, I have to apply X to S. And I cannot just write beta of first and the third component. I should first move this X next to S. So what I should do is I should do a swap operation, which I denote by sigma. Sigma 1, 2, again, recall that notation I use for these indices. This means I'm switching the first and the second component. So this is just a flip applied to the first and second tensor factors. And after this, so when I do this, I'm still in G tensor G tensor G. And after this, I should now do 1 tensor beta, because this is like I got R tensor X tensor S, and now I have to apply the beta here. So end up with R tensor XS. Okay, so now I have to see what maps I got. The first path is the map beta tensor 1 composed with 1 tensor delta. And the second path is the map 1 tensor beta composed with the sigma 1, 2 plus sorry, not plus, but actually composed with 1 tensor delta. Okay, and that is just the first bracket. Now I have another bracket to compute, but let me just put it down here. So I'll just copy it down here. Okay. And now, what about the second bracket? For the second bracket, I should again do a similar calculation. I should draw another diagram and see what I get. And well, I have done this. I don't want to keep you waiting for the result. The result will be plus 1 tensor beta composed with delta tensor 1. So you see the positions are somehow switched, plus beta tensor 1 composed this time with sigma 2, 3, which means I'm flipping the second and the third component composed with delta tensor 1. Okay, so this is the concise way of writing the previous formula, the advantage being that it only describes the connection between the two Lie brackets. Okay, or rather the two maps which play a symmetric role. Beta and delta, they go in the opposite directions. Okay. However, now one thing that's not clear from this definition is that if G comma delta is a Lie bialgebra, well, we can consider G star as the starting point. That also has a Lie bracket that comes as delta star. And then the beta should play the role of the coproduct. In other words, beta star should go from G star to G star tensor G star, and it should play the role of coproduct. Okay, but when you dualize this relation, you don't quite see how beta and delta switch their roles. So this is not quite symmetric looking with respect to beta and delta. And this means that it's not immediately clear that if G delta is a bialgebra, is a Lie bialgebra, that G star with the beta, the Lie bracket, the Lie bracket on G, which is dual of G, like which is dual of G star, is a Lie bialgebra. Okay. So the question is if this is actually true, right? And it turns out it is true, but then we have to take a slightly different point of view towards these Lie bialgebras, from which it is much easier to understand, or rather see, that there's a symmetry between the delta and the Lie bracket. In other words, if G delta is a Lie bialgebra, then G star with the bracket is a Lie bialgebra. Okay, and that is what's called Manin triple. Okay, so we want to kind of give another definition of this Lie bialgebra in the language of Manin triples. And this will also shed light on extra structure, which is very interesting from the point of view of quantization. And that's the motivation for me to talk about this Manin triple structure. So let me first define these Manin triples and then explain why Manin triples are the same thing as Lie bialgebras. So here's what's going on. So here's the definition. A Manin triple is a triple of Lie algebras like P plus, and P minus. 3 Lie algebras and a non-degenerate symmetric bilinear form on P. Maybe I choose a notation for this form right now. Okay, so it's a non-degenerate bilinear form, which is symmetric on this Lie algebra P with the following properties. So the first property is that this bilinear form is P invariant. Now, this means the following relation with respect to the adjoint representation. X, Y, Z plus Y, X, Z equals 0 for all X, Y, and Z in P. Okay, so this is more like I have add X, Y, Z plus Y, add X, Z is 0. Okay. Somehow it says that add X is a skew-symmetric matrix if you choose the notion of transpose according to this bilinear form. Okay. So have you seen this relation somewhere else? Is this familiar to any of you? Yeah? Pardon? Derivation. Yeah, well, in some sense. But what about a bilinear form that's invariant? Have you ever seen any invariant bilinear forms anywhere? For those of you who had studied Lie algebras before. So that's a fundamental object in the classification of simple Lie algebras. And also when you think about cat-smooth algebras, invariant bilinear forms play a fundamental role. So the sort of prototypical example of that is the killing form on any Lie algebra, which is non-degenerate in the case of semi-simple Lie algebras. Okay. How many of you have heard the name killing form? Okay. Anyway, so killing form. It's not about killing anything. It's just the name of a German mathematician. Okay. All right. So that's just for people who might have had some exposure to Lie algebras. Oh, I shouldn't have erased this red formula. That was just another way of thinking about it. But anyway, so this is what I mean by an invariant form, satisfying this relation. Okay. But also, this should remind you of what we discussed in the course earlier. So we talked about, say, the orthogonal group, and the Lie algebra of the orthogonal group was the set of matrices such that x plus x transpose was 0. And you can think about this as follows. If you take the usual inner product on a vector space, then skew-symmetric matrices will be matrices satisfying this property. Okay? And same for unitary matrices and so on. You can write similar relations. So this relation is kind of not, is really very similar to what we've discussed in the course already. Okay? This is the first property. And now what is the second property? The second property that in fact P equals P plus direct sum P minus. So in other words, P plus and P minus are a subspace. Maybe I should say the other way around. Maybe I should say that P plus and P minus are subalgebras, Lie subalgebras. So P plus and P minus are Lie subalgebras of P. And in fact, P happens to be a direct sum of these two, which means every element of P can be written uniquely as a sum of elements of these subalgebras. These guys are not necessarily ideals. This you have to be careful. I'm not assuming they're ideals. They're just two Lie algebras whose direct sum as vector space becomes P. I'm not saying that they are ideals of P. Okay? And the third condition is that they are isotropic subspaces with respect to the symmetric bilinear form, which means that if you pair two vectors in P minus or two vectors in P plus with respect to the symmetric bilinear form, you get 0. Okay, so P plus and P minus vanish when you restrict them to these subspaces. I'm sorry, the bilinear form vanishes when you restrict it to either P plus or P minus. Okay, so such a triple is called a Manin triple. A triple of the algebras P, P plus, P minus, such that P is a direct sum of P plus and P minus as vector spaces. P plus and P minus happens to be Lie subalgebras, but they're not, their bracket is not 0, so they're not commuting. So P is not a direct sum as Lie algebra, as like a, it's not a direct sum of these Lie algebras. I mean, this is not a direct sum of Lie algebras, more precisely. The bilinear form on P is invariant, and P plus and P minus are isotropic subspaces. They just write isotropic. Okay, and now what connects Manin triples to Lie bialgebras is the next proposition. Here's the proposition. There is a one-to-one correspondence between Lie bialgebra structures on a Lie algebra G and Manin triples. P plus P minus, or P minus P plus. What order did I use up there? P plus P minus. Yeah, okay, that's fine. Doesn't matter. Such that P plus is G. Okay, so now how do we prove this assertion? Well, maybe before proving this assertion, now I can explain to you what is the connection, like how do you answer this question using this statement? How do you answer this question? Well, starting from G and delta, we can take the corresponding Manin triple. So it will be basically G plus G star. So and G star. And the reason is that P minus, the reason for P minus being G star is that this bilinear form is non-degenerate. But this isotropic condition implies that the bilinear form is non-degenerate as a map defined on P minus cross P plus. In other words, it results in an isomorphism of P plus with a dual of P minus, or rather dual of P plus being with and P minus. Okay, because this is a non-degenerate form. Okay, the non-degeneracy and these isotropy conditions imply this, that you have a non-degenerate form, and anytime you have a non-degenerate form, you can identify the two spaces involved, one with the dual of the other. We've discussed this before, okay? All right, so now back to here. So G delta corresponds to G plus G star and G star, but now you see that the definition of a Manin triple is symmetric with respect to P plus and P minus. Invariance was with respect to P, and this condition 2 was symmetric with respect to the role of P plus and P minus, and condition 3 was also symmetric. In other words, you can now consider this Manin triple. This is also another Manin triple. And this means that G star with the coproduct that corresponds to this now, which would be this Lie bracket of G, is a Lie bialgebra. So from this picture, the Lie bialgebras on G and G star really are naturally in correspondence, because in the Manin triples, you can switch the role of P plus and P minus. Okay? So from this point of view, that becomes easy. But now we have to see why the concept of a Manin triple is the same as the concept of a Lie bialgebra. Okay? So let's now try to verify that. So what is the idea? The idea is that if we start from a Lie bialgebra, well, I have to construct this Manin triple. But now, as I explained, so I take P to be G plus G star, and I take P plus to be G, and I take P minus to be G star. And now I have to give a bilinear form. So I define the bilinear form to be 0. Of course, I have to define it to be 0 on P plus and P minus. And now, to avoid confusion, I represent the elements of the P minus by X's. Okay, so Xi and Xi prime. So these are definitions. Maybe here I should say Xi and Xi prime and P and X and X prime. Okay. And what about the pairing between X's and X's? So I define xc or cx to be the only thing I can do when I have an element of G star and element of G. I can just apply one on the other. Okay. So this invariance condition needs to be checked. And that's a calculation. And now conversely, starting from P plus P minus, if I have a Manin triple, as I mentioned, this being non-degenerate yields P minus is isomorphic to the dual of P plus. So this means now remember in the Manin triple, P minus was a Lie algebra. It was a Lie subalgebra of P. So now P plus a star is equipped with the Lie algebra structure. And the cocycle relation. So this is again something to check. What I didn't tell you is starting from this bialgebra G delta, Lie bialgebra G delta, how I get a Lie algebra on G plus G star. I didn't tell you yet. Okay. So in order to check that this bilinear form that I defined here is indeed invariant, I need a Lie algebra structure. So I check being a Lie algebra with respect to that. And I also need to make sure that G and G star are Lie subalgebras of this G plus G star as a Lie algebra. Now, this Lie algebra structure is not going to be the usual direct sum Lie algebra structure. Okay, it's going to be more complicated because the invariance needs to be checked. And the invariance will not hold with respect to that. So what is that Lie algebra structure? That will come from the following lemma, which is an interesting ingredient of this picture. So here's the lemma. So the lemma is the following. So now if all the calculations follow from, maybe I should say calculations. The lemma below. So what is the lemma? So assume that G and G star are Lie algebras. And define this bilinear form on, maybe I just write P cross P for P being G plus G star. As above. So it's defined so that G and G star are isotropic subspaces, and the pairing between G and G star is just the evaluation of the functional, just like above. By above, I mean these relations. Okay, I want to take this bilinear form. So now the claim is that So the following are equivalent. Following statements are equivalent. Statements. Okay. So the first statement is that there's a Lie algebra structure on G plus G star such that G and G star are Lie subalgebras of G plus G star, and this bilinear form is P invariant. Here P is G plus G star, of course. And the second assertion is that the Lie brackets of G and G star, note that G star is always the dual of G, make G a Lie bialgebra. Okay, so this is really the crux of the matter. We have to verify that. We have to now give this mysterious Lie algebra structure on G plus G star. So where does it come from? So this we can do with coordinates. So here's the argument of the lemma. So choose a basis like x1 to xn for G, and let C1, Cn be the dual basis. So Xi xj is just delta ij. It's 1 if I and j are equal, it's 0 otherwise. Okay, all is good. Okay. Okay, so now we have the structural constants. So xi, xj, well, I would like to write, I just maybe say this first. I want to suppress all the sigmas, okay? I just avoid writing sigmas. This is what physicists do, and this helps a lot with saving space and like avoiding confusion, okay, in some sense, okay? So I write C, I, J, K, X, K. The only variable without a constraint on the right-hand side is K. So this means there's a summation on K. So there's basically like, I just want to avoid writing this. Okay, this is sigma K. These are like this, like you write the Lie bracket of Xi and Xj as a linear combination of the other X's, because G is a Lie algebra, so we can do this. We still have time, don't we? Yeah, okay. All right. And same with the X's. So again, because G star is a Lie algebra, so we have some structural constants. I denote them by gamma ijk. Again, there's a sigma on K. I'm just avoiding that. Simplify my life a bit. So now, if I want to define a Lie bracket on G plus G star that's compatible with the Lie algebra structures on G and G star, which means G and G star are automatically Lie algebras, then the brackets that I should define on G plus G star on the pairs of X's and pairs of C's should be just like G and G star. The only thing I have to define is what is. So we need to define. We need to define what xi xj is, or rather, oops, c sub r xs. So we need to define these brackets. I mean, if I had xs xr, then I would like to just set it as xc minus xr xs because I want a Lie algebra anyway, right? So we would like to do this. And now, how do we need to do this? Or rather, how can we do this? Well, remember that we have the sort of the invariance of the bilinear form. So we can use this invariance to see what the invariance says about such brackets. So let's start with the following relation. So from the invariance, I can write CR XS CT, and this is the Lie bracket of CR as element of G plus G star with two elements of G plus G star. It should be equal to minus XS CR CT. Right? This is like a invariance, the invariance property, which I had up here, with X being chosen as this C sub R. All right. But now, what is the well, I mean, I want to know, I want to, or rather, I want to define this, okay? And this is some combination of the x's and some combination of the x's. Now, if I want to know the coefficient of a certain x here, well, I should pair it with the corresponding dual vector and see what the number is, and it should be given on the right-hand side, right? Now, on the other hand, what does the right-hand side give me? So the right-hand side, it gives me sigma. Well, I mean, I was supposed to not to avoid sigmas. So here, basically, I have gamma r t k's for all k, but it's multiplied by ck, and the only place where xs ck is non-zero is for k equals s. Therefore, the right-hand side is just gamma r t s. Okay. And this is the coefficient of xt on the left-hand side because it's paired with ct. All right. So this calculation says coefficient of xt in CR XS equals gamma RTS. Completely determined according to the Lie algebra structure on G star. We can also do a similar calculation to determine the coefficient of another CT. Okay, so that calculation is the following. If I write CR XS, yeah, XT. This time I can first switch these two and write this as minus XS XCR XT. And now this time it's the X that moves to the other side. So this will be now a plus because I have to change signs one more time. And I get CR XS XT. And now the coefficients here are like, C, S, T, Ks, but the only time you get something non-zero is K equals R, and that will describe the coefficient of CT in the same product that I was interested in. Okay, so the coefficient of xt in XR xt is CSTR. Okay? Yeah.
In the first one, where does the minus go to? Like in, that's
I think I missed the minus sign. You're totally right. I missed the minus. Yeah. Thank you very much. Exactly. So this one has a, there's a minus I should have kept. All right, so now we actually got an explicit formula for that mysterious Lie bracket we were looking for. Okay, so it follows that psi star, xi star, cr star xs. Or rather, maybe I should say it follows that we should define. I mean, we are forced to define. By invariance, we're forced to define sigma c str xcr xt. Yeah. Minus sigma gamma RT S XT. Okay? So if there was such a Lie bracket, it should be this one. If there was such an invariant Lie bracket on G plus G star, it should have been this one. Now we have to check that we actually got a Lie bracket. Okay? So skew symmetry is really clear from our definition. Because if I take a, like if the Lie bracket on G plus G star, on G, it's just a Lie bracket of G, it's a skew symmetric. On G star, it's a Lie bracket of G star, it's a skew symmetric. And from these formulas, if I switch the role, I just defined it in a skew symmetric fashion, okay? So therefore, the only thing that's left is the Jacobi identity. But again, the Jacobi identity for 3 elements coming from G and 3 elements coming from G star are satisfied, just because I have declared the bracket to be the same as the ones on G and G star. So I have to check some mixed Jacobi identity. So for instance, I have to check some relations. So okay, so we need to verify Jacobi identities like this one. We have CR XS XT plus XS XT CR plus XT CR XS equals 0. Or you might have two x's. Maybe I should say or the one with two x's and 1x. Okay? But now you have explicit formulas for these in terms of the coefficients, the structural constants. Okay? And when you write it out and expand, you see that everything basically reduces to the Jacobi identity of G and G star. Okay? And same for the and also for this relation. Maybe I should say not just Jacobi identity, but also the relation that the two Lie brackets have with each other. So maybe I should also mention that. So also recall. So I mean, so these identities, these relations reduce to Jacobi of G plus Jacobi of G star put together with the cocycle relation. Again, the cocycle relation you can describe in terms of these structural constants. It gives some quadratic relation between the C's and the gammas. Okay. So, I mean, I leave the details as an exercise. It's really not that difficult. It's easier than the other calculations we've done before, but we're kind of maybe short of time. I would like to talk about something more conceptual. Okay. So in fact, what we see here, so there's even more structure. So we just saw that G and G star can be seen as Lie subalgebras of G plus G star, which now became a Lie algebra. Okay, but G and G star were also Lie bialgebras. Okay, so now the question is it possible that they are in fact subalgebras of a Lie bialgebra structure on G plus G star? And even this is also true. So here is the claim. So I'll write this. So now from all that we have seen, we know that the role of G and G star is interchangeable in a Lie bialgebra structure. So really the delta is not important. I just want to say like each of them has a Lie bracket and they talk to each other in some way. So I just write G and G star. Okay. It's now that I know that the role of G and G star is symmetric in a Lie bialgebra, I could just write this ordered pair. Okay. So let this be a Lie bialgebra. And now we now give a name to this G plus G star, which now became a Lie algebra. We call it D of G, and sometimes it's called the Drinfeld double. Okay. And now we pick R in G tensor G star, which I can think of as a subspace of DG tensor DG. Why can I do that? Well, I explained this below. So what is DG tensor DG? Maybe I just write it here. Well, DG as a vector space is G plus G star. And now I know that this operation of tensoring, it's bilinear. So if I tensor a direct sum of two things to the third thing, I could just expand, or rather I use the distributive law of this tensor over the direct sum. And I could do this in both sides. So I get a G tensor G. And the G tensor G star. And the G star tensor G. And the G star tensor G star. Okay. And now I'm interested particularly in this factor, in this summand, not factor, but summand. Okay. So up here, I want to take a certain tensor in this DG tensor DG, which really sits in G tensor G star. Okay. And what tensor? So I want this to be the canonical G invariant 2 tensor. So what do I mean by this? Let me explain. Now this is some like bit of representation theory that's worth knowing. So from vector space, like from, I don't know, from basic linear algebra, we know that for any vector space, V star, for any vector space V, V star tensor V is isomorphic to the endomorphisms of V, the matrix of space. That's just by taking a pair of a linear functional tensor with V to this operator that maps W to, you should be able to tell me what it is. Which operator? Well, it should take a vector W to something. Yeah, what vector? Yeah. That's right. So this is like C of W multiplied V. So rank 1 linear transformation, okay? And now the identity element here, so every time you take a associative algebra, which is unital, there's an identity, a unique identity element. So the identity element should correspond to some tensor here. And how do you get hold of that tensor? Well, one way would be you take bases, a basis for V and a dual basis for V star. So if I take like a V1, VD, a basis for V and a dual basis, like V1 star up to VD star, dual basis for V star, now I can consider this sigma VI star tensor VI. It's not difficult to see that, in fact, this is mapped via this identification to the identity map on V. Okay? So this is this invariant two tensor that I'm talking about. I mean, now this time this G is the vector space V. Well, you could, like, the role of V and V star is interchangeable. I could, I could also use this isomorphism. I could just say V star, V tensor V star. It doesn't really matter. Okay, just flip the factors. And you can also see that this action of G that I defined on two tensors of G, you can also define the same fashion an action of G on the two tensors coming from G tensor G star, and that element will be 0. I mean, that will, like, the action will vanish on this R. So it's an invariant. The concept of the G invariant that I talked about before, it extends to two tensors on G tensor G star or any tensor product of G modules, and this guy becomes invariant. Okay, that's just an interpretation of the fact that the identity commutes with every other linear transformation. Okay. All right. So we take this particular two tensor. Then, okay, so now I kind of, maybe I continue the proposition here. So this was some digression about the decomposition. Okay, so now, what I want to do is I want to equip this DG with a Lie bialgebra structure. So I have to now give a delta. And this delta will be just a coboundary delta. And I gave you a tensor R, which is in DG tensor DG. I just considered the coboundary delta R. So we equip DG with the coboundary delta R, which means delta Rx is just XR. Okay. Maybe I call this like delta sub D. I mean, I don't know. Maybe I shouldn't do this. Maybe. Okay. All right. And now the claim is that then delta R makes DG. Remember, DG was already a Lie algebra with some Lie algebra structure we got in the previous proposition. Now this delta R makes this guy a Lie bialgebra. And the maps that go from G and G star into DG, the obvious embeddings into the first and second components. So these maps are now Lie bialgebra homomorphisms. Well, almost, because, well, you just have to take the opposite of the structure here. So what does the opposite mean? The opposite means if you have any associative algebra or any algebra in general, not even associative, any algebra, you can define the opposite structure, which means the product of x and y is defined to be the product of y and x. Okay, so x, y, you want to define it as yx, yx. Okay, this new product is still distributive over the addition, the vector space of the algebra, so it gives you an algebra of the same type most of the time, almost all the time. Okay, and therefore, and in fact, it is called the opposite structure. Okay. Now, in the case of a Lie algebra, so this means you define the new bracket to be yx, which is minus xy. So there's just a sign difference. And really, in this picture, there's just a sign difference. So it's really small. Okay. Now, what is the outlook? Maybe I use the last 2 minutes to give some outlook. So we talked about some algebraic structures that come in connection with Poisson structures, something that comes from symplectic geometry. And symplectic geometry also plays a fundamental role in quantization. Already, you know, as I explained a little bit in this course, that it's connected to quantum mechanics, classical quantum mechanics, the Heisenberg uncertainty principle, and so on. And then there are also various ways of constructing representations of Lie groups using this technique of quantization. Okay, that comes from like Poisson structures, really. And now there is another sort of type of quantization on a slightly different flavor, but very much connected to what you saw already here. So that kind of quantization starts from a Lie algebra, well, technically a simple Lie algebra, like SL2 or something like this, and it constructs some associative algebra, not over complex numbers, if you start from complex numbers, but over the field of rational functions in one parameter Q with complex coefficients. And so therefore, everything you do in this world, say representation theory or whatever, structure of this algebra, there's always a certain parameter Q. And if you do a suitable Q equal to one limit of this picture, you get all the information about the Lie algebra back. So that's one way to study questions in about like in Lie algebra theory using more refined structure coming from this parameter Q. And the constructions that I described above, for example, the double construction and so on, these constructions have an analog in that world. And they describe the structure of this associative algebra, which is indeed a Hopf algebra. Okay. So in some sense, I gave you a shadow of this quantum group or quantized enveloping algebra UQG by describing these Poisson structures and so on. So this was the closest we could go to the content of the course, which was Lie groups, to sort of get a glimpse of these Hopf algebras, these deformations of the enveloping algebras of the Lie algebras that play a key role in representation theory nowadays. Okay. But there wasn't enough time to really delve into that topic as much, except for the last 5 minutes of the course. Okay, so we can stop now. The final exam is scheduled for the 11th from 7 to 10 p.m. It will be an in-person exam, but you will be allowed to bring electronic devices. So you can bring a laptop or a tablet, whatever you want to do. So the exam is basically in some sort of a open book format. Okay, but you don't have to bring your own notes. Your notes are all electronic, and you can also have, I mean, you can have access to the web. You're not supposed to use your devices to contact anyone else, but you can use this to just search the verb. In a passive way, you can use the information. You're not supposed to sort of use it in a live fashion with anyone else, okay? So that's the idea.
We can only use any apps.
Pardon?
Say just use the PDF.
If you're taking the exam in person, you don't need to submit a PDF. You can just write on paper because it's an in-person exam. If the exam is being printed and being given to you. Oh, PDF viewer. Oh, yes. I mean, as I said, you can use anything on your electronic devices as long as it is not communication with a real person on the other side. I mean, you can also use ChatGPT. I don't know how much it can help you with the exam, but yeah, the exam is in some sense maybe a bit relaxed, but at the same time, you can expect that in the exam I will not be asking definitions or asking you to just write the proof of a statement in the book. Maybe some questions ask you about doing proofs that are analogous to the proofs in the book or the proofs that we did in the class, but I will just not ask standard questions like write the proof of proposition 315, okay? Because this is, you can just copy and paste, which doesn't make sense. Any questions about the exam? All is good? Any questions about the course or anything? Any comments?
Yeah. Will you teach another similar, let's say, will you teach another topic about condensation?
Not next semester, maybe next year, but not next semester. Next semester, I will be just teaching 2 undergraduate courses, second and third year level.
Do you have a favorite book that continues this quantization story in a nice way?
My favorite book would be Chari and Pressley and Janssen's book. So the book by Janssen, Quantum Groups by Janssen, it's more algebraic, but also a bit easier to read because it's sort of more rigorous. The book by Chari and Pressley is really very broad, and many times they only sketch proofs, which is fine. But if you really want a rigorous treatment, either you have to do all the proofs yourselves, which is a very good exercise, or look at other references. So these 2 books, which I already designated as references for the course, are also my favorite books. And you can find the material about bialgebras in chapter, I think part of chapter 1 and part of chapter 2 of that book. So like this is like maybe just 15 pages in that book. I'll be talking in the last 3-4 lectures. But the book is like 700 pages or so. But it's a very nice book. And Janssen's book is more rigorous, but only focused on quantized enveloping algebras, which we really didn't talk about at all in this course, but you might be interested in your research. Any other questions? If not, then enjoy the rest of the semester, and I wish you happy holidays and a great final exam.